Hello friends. So today we are going to discuss the questions from the year 2004, and there are total 3 questions. From the year 2005 we are having 4 questions, and from the year 2006 there is 1 question. So in totality we are going to discuss 8 questions. So the first question, it was asked in the year 2004, and it states that 6 charges, 3 positive and 3 negatives of equal magnitude are to be placed at the vertices of a regular hexagon such that the electric field at O is double the electric field when only one positive charge of same magnitude is placed at R. Which of the following arrangements of charge is possible for P, Q, R, S, T, U respectively? So here the important, you can say, thing to be kept in mind is that the electric field at O should be double the electric field. Okay? And the condition for double is the positive charge of the is placed at R. And we are given the basic figure, and it wants that our R should be having a positive charge, and so we can just, this will be P, Q, R, S, T and U. Okay. And our R should be our positive. It means third charge should be positive. So obviously this C option cannot be true. Okay. And secondly, we want that the electric field at this point O should be equal to the double the electric field that is being generated by the charge which is at point R. Therefore, we can say that our electric field at O, let us suppose call this as EO, should be equal to double the electric field for our R. So basically with O, this EO is the representation of a net, or we can say the resultant electric field. Okay, because if we keep charges at their respective P, Q, R, S, T and U and try to find out the net electric field at point O, then its resultant should be equal to our E naught, or basically it should be equal to 2 times ER. So we can say this E naught is the resultant electric field at center O. So if you want that our resultant electric field is equal to 2 times electric field due to point R, then the electric field because of other charges, that is because of this P and S, which are diagonally opposite with each other, should be balanced. Similarly, the charges which are the electric field because of this T and Q charges respectively should be able to balance each other, such that the net electric field along the line joining this QR should be equal to our 2 times ER. So unbalanced should be only because of this charge at U and charge at R. So we can write that if we want the resultant electric field should be equal to twice multiplied by the electric field at point R. This is only possible when our electric field at P plus electric field at S is equal to 0, and secondly electric field at T plus electric field at Q should be also equal to 0. And we want that the electric field at O should be equal to 2 times ER. And this is only possible if we have that our electric field at R is equal to electric field at U. So under these conditions rather, we are going to get that our electric field at center O will be equal to 2 times ER. Therefore, we start with our P. So we can understand that the charge at P and our S. Let us start with P, and okay, let's do with our R and U, and our R is our positive and U will be our negative. And similarly we are going to get if our U is our negative, so the option that is possible is A cannot be the correct one, then we are left with only B and D, and we want that our P and S. So this is our P, Q, R, S, T and U. So therefore we get that our P will be our negative, and correspondingly our S will be also our negative, and Q is our positive because we are only giving 3 plus 3 charges. There are 3, total there are 6 charges, so we have 3 plus 3, so Q is our positive and T will be also our positive. Okay. So only option D is the correct one. You can say option D is correct. Next question. It was asked in the year 2004, and it states that a capacitor is charged using an external battery with resistance X in series. The dashed lines show the variation of natural log of I with respect to time. If the resistance is changed to 2x, then the new graph will be. So we can divide this question based on 2 parts. In the first part, we are given that we have a capacitor and it is being charged through a battery using a resistance X, and this is our capacitor C. Let us suppose this is potential V. And in the second case, now the resistance has been changed to 2x. So we can just, this resistance is our 2x, rest of the parameters are same. So this is our capacitor and this is our V. And we know that the current for when the capacitor is charging, so we already know the equation. So we can say for capacitor C charging, we know that our I is equal to I naught e raised to power minus t upon RC. I naught is our maximum current, which is our V upon R. So we can write this as our I is equal to V upon R e raised to power minus t upon RC. Here this RC nothing but our time constant. And we need to find out the natural log of I. So if we take natural logarithm for the both sides, we get this as natural log of I is equal to natural log of V upon R, and this comes as minus, this is t upon RC, and natural log of E, and it can be further simplified as natural log of V upon R minus t upon RC. And here this is nothing but, let me write it separately. The natural log of I is equal to natural log of V upon R minus t upon RC. So we can write this as a in the form of a slope as well as the intercept. Okay, so from here we can say that our slope will be equal to minus t upon RC, and the intercept is equal to natural log of V upon R. And in the first case, our R is equal to X. So we can write for case 1, we have our R is equal to X. Therefore, we can say that its slope will be equal to minus t upon XC, and the intercept will be equal to natural log of V upon X. In the second case, our resistance is now doubled, so which gives us that the slope will be equal to minus t upon 2XC, and intercept will be equal to natural log of V upon 2x. And from here we can clearly see that both the slope as well as intercept are decreasing. Okay. Therefore we can say both our slope and intercept decreases, and we are only talking about the magnitude part. And both slope and intercept decrease. Therefore we can say that this P is the representation of the new graph. Okay, so this Q, sorry, not P but Q, and we can say option number B is the correct one. Option B is correct. Next question. It was also asked in the year 2004, and it states that there are two large parallel metallic plates S1 and S2 carrying surface charge densities sigma 1 and sigma 2 respectively, where sigma 1 is greater than sigma 2, placed at a distance d apart in vacuum. Find the work done by the electric field in moving a point charge q through a distance a where a is less than d from S1 towards S2 along a line making an angle of pi by 4 with the normal to the plates. And here we are given that we have a two large parallel plate S1 and S2. So we can just draw an approximate figure. Suppose this is our S1 and this is S2. Distance between the two is given as capital D, and S1 is having a charge density of sigma 1, S2 is having a charge density of sigma 2, and we have to remember that sigma 1 is greater than sigma 2, and we are moving a point charge from S1 towards S2. Okay. So it means we are moving point charge Q is moved at distance A from S1 towards S2. So from S1, point charge is moved through a distance of A, but it is moved along a line which is making that angle of pi by 4. So if this is our straight line, then the charge is moved by angle of pi by 4. Okay. Angle is given as with the normal to the plates. Okay, 1 second. So it states that making an angle with the normal to the plates. So if this is the normal to the plates, then we are moving the charge Q at an angle of pi by 4. So charge is moved in this direction, that is point Q charge. And we have to find out the work done. So in this case, we know that the electric field because of single plate is sigma upon 2 pi epsilon naught, and we are having two plates, and in between the plates it will be nothing but, we are only interested in finding out their magnitude. So we can say it will be our sigma 1 minus sigma 2 and divided by epsilon naught, and work done we know is our F multiplied by D, that is FD cos of theta, and F is our Q multiplied by electric field. So we start from the basic formula, that electric field, we have to first of all find out the net electric field inside the plates, because charge is being moved only inside the plates. So we are interested in the electric field which is inside the plate. So we can say net electric field between the plates, and electric field due to plate S1, electric field due to plate S1, let us suppose that is our E1, this is equal to sigma upon 2 pi epsilon naught, and we have to remember that electric field due to this plate, there is no you can say mention of the how much distance that charge has been moved, because in the question it is given that it is being moved by a distance of A. So this electric field is not dependent upon the distance, it is only dependent upon the charge density as a constant as epsilon naught. Similarly, we can find out the electric field due to place S2, suppose that is given as E2, so it will be equal to over sigma 2, and we have 2 epsilon naught, and we are given that our sigma 1 is greater than our sigma 2. Therefore, net electric field net electric field, if it is given as our E net, will be equal to E1 minus E2, and we can substitute the second. Okay, so we can write it as our E net will be equal to, we have this as sigma 1 minus sigma 2, and this is our 2 epsilon naught plus sigma 1 minus sigma 2 divided by 2 epsilon naught, and this gives us sigma 1 minus sigma 2 and divided by our epsilon naught. And we can also, you can say, define it I think this will work. There is no need to further definition. Now we can find out the, you can say, the force on the point charge and if that force is given as F, then this F is equal to Q multiplied by our E net. This gives us that our force F will be equal to Q sigma 1 minus sigma 2 divided by epsilon naught. Now we can easily find out the work done. Work done by the electric field, and let us suppose that is given as W. Then this W will be equal to our F, and this is our D effective distance, and we have this as cos of theta. So here our D effective, this is the distance, effective distance moved. Effective distance moved, and which is nothing but our A, and our theta is the angle between the two, that is in this case is pi by 4. Therefore we can write that our work done will be equal to our F A cos of pi by 4, and we can easily substitute value of our force. We get this as Q sigma 1 minus sigma 2 upon epsilon naught multiplied by A, and cos pi by 4 is square root 1 by square root of 2. So now it is almost done. So we get our work done is equal to Q times A sigma 1 minus sigma 2 divided by square root of 2 and its epsilon naught. So So this is the work done by the electric field. Next question. And it was asked in the year 2005, and it states that 3 infinitely long charge sheets are placed as shown in figure. The electric field at point P is, and we have to find out the electric field at a point. In the previous question we also discussed that electric field is independent of the distance of the point. It is only dependent upon the charge density, okay, and epsilon naught, that is a constant value. So you can say the electric field due to infinite plane sheet of charge is independent of the distance of point from the sheet. Therefore, we can simply use principle of superposition. Principle of superposition. We can write electric field at point P will be equal to electric field because of the Z is equal to 3A plus electric field because of Z is equal to 0 and plus electric field Z is equal to minus A. And we are simply going to substitute there. So we get the first case, it is given sigma. So this comes as sigma upon 2 pi epsilon naught, and with minus of k unit vector, plus next is our 2 epsilon naught, and this is our 2 sigma 2 epsilon naught, and this comes as minus of k plus sigma upon 2 epsilon naught, and this comes as minus of k. And we can easily take sigma upon 2 epsilon naught minus of k as common. So we get this as 1 plus 2 and plus 1. And this comes as 4. 4 is, so this will be equal to 2 sigma upon epsilon naught and minus k unit vector. So we get this as 2 minus 2 sigma k epsilon naught. So option number B is the correct one. Option B is correct. Next question. It was asked in the year 2005, and it states that a 4 microfarad capacitor and a resistance of 2.5 mega ohm are in series with 12 volt battery. Find the time after which the potential difference across the capacitor is 3 times the potential difference across the resistor, given that natural log of 2 is 0.693. So we can just draw the approximate figure. So we are given a resistor and a capacitor, they are in series and connected with the battery. That is, for the EMF is E, and this is our R and C. So this is our series RC circuit. And we already know that our suppose the voltage drop across R is our VR and voltage drop across capacitor is our VC. Therefore, we can write that our EMF E will be equal to VR plus VC. And we also know, or rather we can say, we are given in the question that the potential difference across capacitor is 3 times the potential difference across the resistor. Therefore, we can write that our VC is equal to 3 times VR. So we substitute, we get this as E is equal to 3 times VR plus VR, and that will be giving 4 times VR. So from here we can say that our VR will be equal to voltage EMF E divided by 4. And we also know that the expression for the voltage across the capacitor, you can say our VC at any time t will be equal to the EMF, and this comes as 1 minus E, and this is minus t upon tau. And our VR at any time t will be equal to EMF, and this is our E minus t upon tau. Here tau is our time constant, which will be equal to our R multiplied by C. We already know our value for R and C, so we simply calculate it. We get T is equal to R is given as 2.5 mega ohm. This comes as 2.5 into 10 to the power 6. Capacitor is given as 4 microfarad, 10 to the power minus 6. Therefore, we get our time constant will be equal to 10 seconds. So we can use the relationship with respect to resistance, and we get that our VR at any time t is equal to EMF e raised to power minus t upon tau, and VR we just found out is our EMF upon 4, EMF e raised to power minus t upon tau. Tau is our 10 second, and here this EMF and EMF cancels out, and we get this as e raised to power minus t upon 10 is equal to 1.4. So this we can write that minus t upon 10 is equal to natural log of 1 by 4 which will be minus natural log of 4. So write this is minus t upon 10 is equal to minus natural log of 4, and here minus and minus goes away. So this comes as t will be equal to, this comes as 10, and we can write this as 2 natural log of 2. Value of natural log of 2 is given as 0.6269, sorry. So this comes as 10 multiplied by 2 into 0.693. So we get our t is equal to 13.86 seconds. So option number A is the correct one. Option A is correct. Next question. It was asked in the year 2005, and it states that a conducting bubble of radius A, thickness T, has a potential V. Now the bubble collapses into a droplet. Find the potential on the droplet. So in this case, we have to remember that there is a change of shape from bubble to a droplet, and during this process two things will remain conserved. First is that you can say the charge is going to remain conserved. You can say our charge is conserved, and the volume will be constant. Volume of the liquid remain constant. Volume of liquid remains constant. So let us find out the volume of the liquid in the bubble. Volume of liquid in bubble, let us call that as V liquid, will be equal to the surface area multiplied by thickness. So we can write our volume of liquid will be equal to 4 pi a square multiplied by thickness, that is given as T. Now we can find out the radius of the droplet because the volume is to be same. So we can say that radius of droplet, let us call that as R prime. Therefore we can write that the volume of droplet let us call that as Vd, will be equal to 4 by 3 pi R prime and its cube, and the volume of the droplet is equal to volume of the liquid in the bubble. Therefore we can say that VL is equal to Vd, and we can just substitute the values. VL is our 4 pi a square multiplied by thickness T is equal to 4 by 3 pi R prime cube, and here this 4 and pi cancels out, So we can write that our R prime will be equal to, this will be coming as 3a square t and whole raised power 1 by 3. So this is the radius of the droplet, and we can find out the charge on the bubble in terms of the potential. So we can say potential on the bubble potential of the bubble, let us call that as VB, and let me write this as capital B. This will be equal to K Q divided by A, and this Q is the charge on the bubble. So this Q is the charge on bubble, which can be written as VB multiplied by A divided by K, and the charge on the bubble as well as the droplet will be same because of the conservation. So we can write that our potential on, we can also say charge on the droplet, charge on droplet will be equal to charge on the bubble, charge on bubble, which is equal to Q. Now we can simply write the potential of the droplet. Potential of the droplet, let us call that as V prime, that will be equal to K charge, that is Q divided by R prime. We can easily substitute value of Q as well as R prime, so we get our V prime will be equal to K, and Q we just found out is our VB multiplied by A and divided by K, and our R prime is our 3a square t and whole raised power 1 by 3. So this K cancel with K, so we get this is equal to VBA divided by 3a square t and whole raised power 1 by 3. And we only term which is common, numerator denominator is our A, the rest of things we can just sort it out. So this comes as VB divided by 3t 1 by 3, and this comes as A, and this will be our A and 2 by 3. So we can just easily solve this our A part. This will be coming as 1 minus 2 by 3, which will be automatically equal to 1 by 3. So we get our V prime will be equal to our VB divided by 3t 1 by 3, and this comes as our A and our 1 by 3. We can just club because here power is same for 1 by 3, so we can write this as our VB, and this will be our A 3t, and we have 1 by 3. This is our okay, and here the potential is given as V, so therefore we can put VB is equal to A. VB is equal to V. So we get our V prime is equal to V, and this comes as our A 3t and whole raised to power 1 by 3. Next question. It was asked in the year 2005, and it states that at t is equal to 0, switch S is closed. The charge on the capacitor is varying with time as Q is equal to Q naught 1 minus e raised to power minus alpha t. Obtain the value of Q naught and alpha in the given circuit parameters. So here this is basically our RC circuit, but RC circuit, a combination of RC circuit, but the circuit is drawn a little bit different. We have a capacitor C and in parallel with the resistance R2, and this entire circuit is in series with our resistance R1. Okay, so the circuit is drawn a little bit different way. And this equation for the charge on the capacitor is quite standard one, which is given as Q is equal to Q naught 1 minus E, and this comes as minus alpha times T. And here Q naught is our maximum charge on the capacitor. So this Q naught is our maximum charge on capacitor. Okay. And where we can find out the charge on capacitor, because this capacitor is in parallel with R2. So therefore we can write that this value of Q naught will be equal to C multiplied by V equivalent, and here this V equivalent will be equal to voltage across the capacitor in steady state condition. So this is our voltage across capacitor in steady state condition. And the charging of the capacitor, the equation which is given, in general it also involves a time constant that is given as our tau, because of a simple RC circuit. And we can say our tau is our time constant, and in general this formula is our R multiplied by C, and this particular equation is only when we are having one value of R and one value of C. But in the given question we are having two values of R, R1 and R2. Therefore we can generalize the time constant formula as our R equivalent. Okay, we'll drive that later on, what will be our R equivalent. And we can simply make a comparison, and we can say that our value of alpha will be equal to 1 upon our time constant. So let us find out first of all what happens under steady state condition. So under steady state condition, which basically means that t tends to infinity. Steady state condition means t tends to infinity. Capacitor acts as an open circuit. Capacitor C, this will be acting as a open circuit. So we can just redraw the given figure. So we have R1, R2, and switch is closed, and the voltage is given as V, so switch is closed. Okay, and capacitor is acting as open circuit. So this is the basic circuit. So from here we can find out the steady state current. Let us suppose we call this as I steady state. So this R1 and R2 in series. Therefore we can write that our steady state current ISS will be equal to V divided by R1 plus R2. And we need to find out the voltage across this capacitor, which is here acting as open circuit, and this capacitor is in parallel with R2. So voltage drop across R2 will be same, that is the voltage across the capacitor. So we are interested in finding out the voltage across R2. So you can say voltage across R2, let us call this as VR2, and we can say that our VR2 will be equal to steady state current multiplied by the resistance, that is our R2, and we substitute the steady state value. We get this as V times R2 divided by R1 plus R2. And like we said, that the voltage drop across capacitor, which is, let us suppose, our VC, this will be same as our VR2, which gives us a VR2 R1 plus R2. And we need to find out the maximum charge. You can say our maximum charge Q0 will be equal to C multiplied by voltage across the capacitor, V voltage across our R2, and C, this comes as V R2 R1 plus R2. So this was our first part, obtain the value of Q0, and we need to find out alpha. Alpha is nothing but time constant. So alpha is not a time, alpha is 1 upon time constant. Alpha is 1 upon time constant, and like we said, this time constant, tau will be equal to R equivalent multiplied by C. And in order to find out this time constant, we are going to short circuit our voltage source. So voltage source is short circuited, and we have these two resistances, this is our R1 and R2, and we have our capacitor here. So from the circuit we can clearly see that this R1 and R2 are in parallel. So we can find out our R equivalent. So R equivalent will be equal to R1 into R2 divided by R1 plus R2, which gives us that the time constant will be equal to C times R1 R2 divided by R1 plus R2. And we need to find out our alpha, which is 1 upon time constant. So we can say alpha is equal to 1 upon C R1 R2 R1 plus R2. This gives that alpha is equal to R1 plus R2 and divided by C multiplied by R1 times R2. And here I equivalent we are going to find out by looking inwards across these two terminals. Okay, that's why this R1 and R2 are in parallel. Next question. It was asked in the year 2006, and it states that find the time constant for the given RC circuit in correct order in microsecond. So we have three circuits. Let us call this as A, B and C. And it says that this is a RC circuit and time constant for our RC circuit is equal to R multiplied by C. And this formula is only true for one value of resistance and one value of capacitance. This is only for R and C, and they should be in series. In the given circuit A, B and C, we have two values of capacitors as well as two values of resistance. Therefore, we can modify this time constant formula. The time constant, we can write this as for RC circuit. We are going to write this R now as R equivalent and this C also our C equivalent. So this is the general formula for our RC circuit. And in order to find out this time constant, one of the basic, you can say, step is that we have to short circuit first of all the voltage source. Okay. So for circuit A, if we short circuit the voltage source, so we have our R1, R2, C1 and C2. So our R equivalent will be a series combination of R1 and R2. Therefore, we can say that our R equivalent is our R1 plus R2. R1 and R2 are given as 1 and 2. So this comes as 1 plus 2. So we get our R equivalent is equal to 3 ohms. Similarly, we can find out our C equivalent, and C equivalent is the parallel combination of C1 and C2. So we can write that C equivalent will be equal to C1 C2 divided by C1 plus C2. And once again, oh sorry, the C1 and C2 are in parallel, not in series, my mistake. So C equivalent will be equal to C1 plus C2, because in parallel it is direct addition, which is reverse of our resistances. So C1 and C2 are given to us 4 and 2. So this comes as 4 plus 2, which is our 6 microfarad. Therefore, we can say time constant for circuit A is equal to our 3 multiplied by 6. And this is our 3 ohm and 6 microfarad. Time constant is to be found in terms of the microsecond. Okay, need not to convert. So this comes as 18 microsecond. We come to the circuit B. And circuit B is our C1, C2 in series, R1, R2 in parallel. So we have our C1, C2 in series and R1, R2 are in parallel. So we can write here our R equivalent will be equal to R1, R2 divided by R1 plus R2, which is our 1 multiplied by 2 and 1 plus 2, giving us 2 by 3 ohm. And our C equivalent C equivalent is in series. So series comes as C1 C2, C1 plus C2, which is 2 and 4, 2 4 and 2 plus 4. This comes as 8 divided by 6, and it will be coming as 4 by 3. Therefore, time constant for circuit B is our 2 by 3 multiplied by 4 by 3. Which will be coming as 8 divided by 9 microseconds. And finally, we have our circuit C. So for circuit C, we are given both are independently parallel. So we have R1, R2, C1, C2. Therefore, we can write our R equivalent will be equal to R1, R2 divided by R1 plus R2. Parallel combination is sorted out. That is our 2 by 3. And our C equivalent, where the C1 and C2 are parallel. So this will be coming as C1 plus C2, and we just found out is equal to 6 microfarad. Therefore, we can say the time constant for our figure C will be equal to 2 by 3 multiplied by 6, and this goes by 2, so we get this as 4 microseconds. And so we have this as A is our 18, so this is our 18 and this is our 4, and this is our 8 by 9. I think 8 by 9. Yeah, 8 by 9. So we get option B is the correct one. Option B is correct. Yes. So this completes the questions, total 8 questions, and we were having this from 2004, questions were 3, 2005, questions were 4, and from 2006, the number of questions were 1. So this completes all the 8 questions. Thank you.